Hello my dear students, welcome to the online class. Myself Muhammad Anas, I am a physics faculty. So today we will discuss the chapter electric potential and capacitance from your second year syllabus. I hope you already gone through the chapter electric charges and fields. Once you know the concept of electric charge, electric field and electric force, then this chapter electric potential and capacitance is very easy. So in this chapter, the very first question I would like to ask you about the concept of electric potential. What is potential? Can you say that? Okay, let me give you the idea. So first of all, we will discuss the concept of electric potential. Electric potential, or we can say that electrostatic potential. Suppose we are having a charge, it's a point charge which is initially at rest, it's a static charge. We will select a point at a distance small r from this charge, from the point charge that we selected. Now suppose we are having a unit positive charge initially placed at infinity. When we provide some force on that unit positive charge, this charge will move and comes to this point. Now what is happening? Now we can say that we are doing a work to take the charge of unit positive strength from infinity to this point. That work done is called electric potential. So what is electric potential? Electric potential is the work done by an external force to bring a unit positive charge from infinity to a point. So that point is in the electric field of a source charge. So let me give you the idea. Now we are having a charge and there is a point at a distance r from the source charge. Then potential at this point, or the work done to move a charge from infinity from this to this point is given by the equation V is equal to 1 by 4 pi epsilon q by r square. We can use this equation. This is the value for potential produced by a unit positive charge. Suppose you are placing this charge in a free space, then this value will be epsilon naught. Epsilon naught, it is the permittivity of free space. Now this is what we call potential due to point charge. Potential due to point charge. Okay, now we are having a source charge. We are having a source charge and we are having 2 points. There is a point A and another point B. Look at here. From this source charge to point A, we have a distance r1. From the same charge to point B, we have another distance r2. Now what we are going to do is we are simply taking a charge q, another charge q, or another charge from this region to this region. We are taking a charge from this region to this region. Then we will have to do some work. Before that, let me give you an idea of this is point A. This point A is having a potential VA and this point B is having a potential VB. Then we can find the potential difference between A and B. What is potential VA? It is 1 by 4 pi. Let's say this charge is placed in a free space. Then VA can be written as 1 by 4 pi epsilon 0 q by r1. At the same time, VB is given as 1 by 4 pi epsilon 0 q by r2. Now we have to find the potential difference. Potential difference VAB, we can write down VA minus VB because VA is the higher potential. The distance is less than that of R1 is less than that of R2. So that's why we take VA is the higher potential, VB is the lower potential. then what is the potential difference? Look at these two terms. We will take the common term 1 by 4 pi epsilon naught outside. Then we will have 1 by r1 minus 1 by r2. So this is the potential difference of any 2 points. If you select a conductor, or if you connect a conductor from A to B, an electric current will starts to flow from A to B, because A is having higher potential, B is having lower potential. So this is potential due to point charge. This is potential difference due to a point charge. Now let me give you one more idea. This potential can be written as work done to bring a unit positive charge. We can do this. Then what is potential difference VAB? Potential difference VAB, we know that VA minus VB. It is nothing but, if you have a charge plus 1 over here, if you take this charge from B to A, look at here, you are taking a charge of unit positive strength from point B to point A. Then you will have to do some work. That work is given as WBA, work done on a unit charge to take it from point B to point A. So this potential difference can be also written as work done per unit charge. Look at here, we need these equations, very very important. Please try to note down what is an electric potential and what is the potential difference between 2 points due to a point charge. So the very next idea we have to discuss is about potential due to a dipole. What is a dipole? Dipole is nothing but two charges of equal magnitude but opposite polarity. This is a dipole. There is a plus q, there is a minus q. Maybe I will take this as minus q, maybe this is plus q. They are separated by a very small distance. This is what we call a dipole. If this is the midpoint of a dipole, then this distance is given as a. We will take it as small a, and the other distance is also taken as small a. We have this. Now we will select a point over here. This point, if we draw a line joining to that point from the center of the dipole, we can see that the distance is r. And this line joining is making an angle theta with respect to the length of the dipole. Then potential at this point V, it is equal to 1 by 4 pi epsilon 0 p cos theta divided by r square. This is the equation we have to know about a potential due to a dipole. It's a very general idea where theta is the angle between line joining of a point to the center of the dipole, and it is making an angle. What is theta? Theta is the angle made by the line joining with the length of the dipole, and r is the distance measured from the center of the dipole to that point. Now if theta is 90 degree, this point will align along the equatorial line. That is, we can take it as equatorial line. What is an equatorial line? This is an equatorial line, a line passing through the center of the dipole. We can call it as equatorial line. In this equatorial line, if theta is 90 degree, you can see from the figure, therefore cos theta is 0, because cos 90 is 0. That means there is no potential at all. If you select any point in this equatorial line where the potential seems to be 0. Now if theta equal to 0 degree, then cos theta will be 1. If theta equal to 0, we will have this line. What we call that? We can simply say it as axial line. Okay, so then For axial line, then for axial line, cos theta equal to 1, since theta is the angle, that would be 0. If cos theta is equal to 1, then the potential will be 1 by 4 pi epsilon 0 p by r square. What is p? P is called a dipole moment. Dipole moment of the given dipole, whose magnitude is given by, it's a vector quantity whose magnitude, it is nothing but magnitude of charge with the length of the dipole. Length of the dipole is 2a, magnitude of the charge is q. So p is nothing but q into 2a. We can say that. Another thing we need is the direction of p. Direction of p is always from negative charge to positive charge, but we don't need direction here. Please try to figure it out. And one more thing I would like to note is the SI unit of potential. What is SI unit of potential or potential difference? Potential or potential difference. Yeah, it's nothing but volt. This potential difference we can also term as voltage. Okay friends, now we will discuss the concept of potential due to a uniformly charged spherical shell. What is a shell? Shell is nothing but a hollow conductor. Inside and outside are air, and the surface, it is made up of some metal. You have seen bulb. Bulb is nothing but a shell. Egg, you can see egg shell. So what is shell? Shell is nothing but material having composition of matter only at the surface. Inside is hollow. Then we call it as a shell. Now we are having a shell. I can mark the shell like this. It's a spherical shell. And it is uniformly charged also. It is uniformly charged. Okay, no problem. It is uniformly charged. Now we will select 3 points. Point A, it is inside. Point B, on the surface. Point C, outside. No problem. We are having 3 points. Now, first we will discuss potential at inside point. Potential at inside. That is point A. We can mark it as VA. It is nothing but 1 by 4 pi epsilon 0. Suppose the total charge distributed over the shell is Q and the radius of the shell is R. It is nothing but 1 by 4 pi epsilon 0 Q by R. Now potential at the surface, that is point B. When we come to point B, what we can see is the potential VB, it is given by 1 by 4 pi epsilon 0 Q by R. From these two relations, we can say that potential of any point inside and the surface of a shell are the same. So if you select a point over here, if you select a point at the center, if you select a point on the surface, whatever the point, any inside point and any surface point are having same potential. If I select a point over here, that is of point D, the potential is same as that of A, which is same as that of B. Only the change in potential occurs at a distance outside, at a point outside. You can see that there is a point outside at a distance of small r. Then we can write down potential at outside, that is point C. You can see point C, that point C is separated by a distance r from the center of the shell. then the potential Vc can be written as 1 by 4 pi epsilon 0 q by small r. Now if you draw a graph like this, that graph simply plots distance with the potential or voltage, or we can say that distance with the potential. If you start from the center to a distance r, the potential is constant. After that, the potential reduces. At this point, the potential is given by 1 by 4 pi epsilon. We can also we can take this term also as k. So k q by r. It's a fixed value, any inside point or any outside point. Now, if you come to the region, it is the distance which is greater than that of r, it is equal to kq by small r. So, inside any point to the surface, potential is constant. Thereafter, potential reduces. Okay, now we will discuss potential due to a non-conducting solid sphere. Now, in previous part, we have discussed potential due to a uniformly charged spherical shell. For a uniformly charged spherical shell as well as for a uniformly charged conducting sphere, the equations are the same. But if you select a non-conducting sphere, equations will change, and we will discuss how it changes. If you select a non-conducting spherical shell, that means charges are distributed randomly as shown. Look at here, charges are distributed randomly as shown. Now we select a point inside. That point is having a distance r, no problem. R is the distance. Then maybe this is point A. We can say that potential at inside, that is point A. At point A, you can see the equation is very simple. It is given by 1 by 4 pi epsilon 0 3 r square minus small r square divided by 2 r cube, where capital R is the radius of the non-conducting solid sphere and small r is the distance that we measured to inside. Now we select a point over here, that is B. We can say that potential at the surface, potential at the surface, potential at the surface, that is point B. We can say that VB is nothing but 1 by 4 pi epsilon 0 total charge present in the sphere divided by square of the divided by the radius value. This is what we can use over here. No problem at all. Very easy task. Now when you select a point C, I am taking this point C also having another distance r. Look at here, maybe we can call it as r dash, no problem. Then potential outside the, that is point, we can take point C. This is point C. Then the potential Vc is nothing but 1 by 4 pi epsilon 0 q by r dash. So these two are very easy to calculate. But inside the non-conducting sphere, potential is not equal to that of the surface. It will follow an equation VA equal to 1 by 4 pi epsilon naught 3 r square minus r square divided by r cube. This r is the distance to that point from the center of the sphere. Okay. Okay students, now we will discuss the concept of equipotential surface. Equipotential surface. Equipotential. So what is equipotential? Which means same potential. If you select a surface, in that surface, every point, if this is a surface and you take 3 points on the surface A, B and C, if potential at A equal to potential at B equal to potential at C, then we call it as an equipotential surface. Every current carrying conductor is an equipotential surface, which means in that conductor every point are having same potential. Since we have an equation VA minus VB equal to VAB by Q, then what is the work done to move a charge Q from A to B? Work done to move a charge from A to B is given by VA minus VB divided by Q, into Q. Now you look at here, if VA and VB are the same, you can move the charge without any work. So at the equipotential surface, work done to move a charge from one point to another is 0. We don't have to do any work on that equipotential surface. So we can find this 0. Another thing is, in the equipotential surface, electric field lines are always normal to that surface. Always normal to that surface. Electric field lines, which is simply leaving the surface, are always normal to the surface area that I drawn like this. So electric field lines are always normal. There is no need to do work on the equipotential surface to move charge from one point to another. Another thing we can say that in an equipotential surface, electric field intensity, it's a vector quantity that is given by minus of del into potential. Del is an operator. That operator is, we can represent by dou x of I plus dou x of dou y of j plus dou z of k. Dou is a partial derivative. Partial derivative means a function which depends more than two variables can be differentiated by using this variable. Or I can give you another equation. Electric field can also written as, look at here, very easy idea. We can write down EXI plus EYJ plus EZK, because it's a vector quantity. Now we have an equation, electric potential is equal to negative, look at here, negative of potential gradient. We have this equation. This is applicable for equipotential surface. When the distance increases, electric field decreases. That is why there is a negative sign. So electric field intensity is the negative of derivative of potential with respect to distance. So we can write down, look at here, very easy. Electric field at the x-axis can be written as dV by dx into I plus dV by dy into j plus dV by dz into k. In some questions they will give you the potential and they will ask you to find the value for electric potential, no problem. Now let me give you one more idea. If you know this equation, we can write down, look at here, let me give you this idea, E is equal to minus dV by dr. Then what is dV? dV is equal to minus of E dr. So if you want to move a charge from a distance r1 to r2, you integrate this function, you will have minus of r1 to r2 E dot dr. So if you know the electric field, if you integrate that electric field from a distance of r1 to r2, you can find their potential difference. It's a potential difference, okay? Potential difference. So guys, please note down these equations. This is potential difference between a point of distance r1 to r2 from the source charge. Now we have to know what is electrostatic potential energy. We will go to the idea of electrostatic potential energy. Suppose we are having two charges, Q1 and Q2, and they are separated by a distance r, then the potential energy, the mutual potential energy between them is given by 1 by 4 pi epsilon 0 q1 q2 by r only. This is we call potential energy. Now look at here. Here we can also write down V1 into Q2. What is V1? V1 is the potential due to this charge at this point. Potential due to Q1 at this point. What is their value? 1 by 4 pi epsilon 0 Q1 by R. So if you multiply this potential with the second charge, you can find the potential energy gained by the second charge. Or this you can also write down V2 into Q1. What is V2? The potential due to this charge over this point, that is equal to 1 by 4 pi epsilon 0 Q2 divided by R. So now you multiply Q2 with the Q1, you will have this relation. So look at here, potential energy, it is equal to potential into charge at that point. That is the equation. Similarly, potential energy difference, it is equal to potential difference into that charge. Let me explain that idea. Suppose you are having a point A, another point B. You will move a charge from A to B. You will move a charge Q from A to B. So you can done a work WAB. This is the work done to move a charge from A to B. Then you can write down that work done WAB, it is equal to potential energy at A minus potential energy at B. So this work done is equal to change in potential energy. It can be also written as charge into potential at A into potential at B. So guys, this is the relation between work done, potential energy difference, and that potential energy difference is nothing but potential difference into the charge. Okay guys, so consider a system of 3 charges as shown. They are in a triangular arrangement. You can see their separation. Now the total potential energy of any charge can be written as U12, U23, U31, because there are 3 individual potential energies. We can write down 1 by 4 pi epsilon 0, the 2 charges are Q1 and Q2 divided by R12, 1 by 4 pi epsilon 0 Q2 Q3 divided by R23. Similarly, 1 by 4 pi epsilon 0 Q3 Q1 divided by R13. So you add the individual potential energy of every system, individual systems, you will have the total potential energy of the combination of the charge. Okay, very important idea. Okay, the another idea we have to discuss is the potential energy of a dipole which is placed in a uniform field. So what is a uniform electric field? If the field lines are parallel, we say that it's a uniform electric field. In that electric field, we place a dipole like this. There is a minus Q, there is a plus Q. This is the position of the dipole. Length of the dipole is making an angle theta with respect to electric field intensity. Now there are 2 vectors. One of the vector is dipole moment. Direction of dipole moment is from minus Q to plus Q. I draw like this. This is our dipole moment. And another vector is E. E is the vector. It is parallel, it is horizontal. So the dipole moment is making an angle theta. Then potential energy of the dipole is written by minus of PE cos theta. Or we can write down minus of P dot E. This is the equation we can use for find potential energy of a dipole. Let me give you. If theta is equal to 0, we say that the both vectors E and P are parallel. Okay, this is called a stable equilibrium. This position is called a stable equilibrium. Please note down, this is stable equilibrium. Here potential energy is very minimum. We know that if cos theta equal to cos 0 equal to 1, we will substitute that 1 over here. We can have the minimum potential energy PE. So for a dipole which is having a minimum potential energy only at the position of stable equilibrium, if theta equal to 90 degree, cos 90, that would be 0. Therefore, if the dipole is arranged perpendicular to the field, if the angle between them is 90, then there is no potential energy at all. Okay, now if theta equal to, what does it say? 90, after that we apply 180 degree. That means the dipole is arranged just opposite to the direction of the field. They are having a 180 degree apart arrangement. Cos 180 is equal to minus 1. If you substitute that thing over here, you will get the maximum potential energy, that is called plus PE. And this is called the position of unstable equilibrium. Unstable equilibrium. Very, very important idea. Okay. Suppose we rotate a dipole. Suppose we are having a field E. Initially, an electric dipole of dipole moment P, it is placed at an angle theta 1. When we rotate this dipole to another angle theta 2, we can see that we have done some work on the dipole to displace it. So, to rotate, rotation is from where? Rotation is from theta 1 to theta 2. Then the work done is given by, look at here, very easy idea. It is nothing but PE into cos of theta 1 minus cos of theta 2. This is the work done to rotate a dipole against the field from an angle theta 1 to theta 2. So please try to understand this idea. Okay.